In this presentation I will show you the challenges of EV charging, and I'm talking about implementation in grid calculation tools. I am Ernest Wierenga, I'm working at Stedin and I'm responsible for protection and for PowerQuality. Stedin is a grid operator in the most of Randstad, but also in Utrecht. So now coming to the contents. I guide you in some introduction, challenges increase of PV and EV, emission limits, implementation of grid calculation tools, and at the end a wrap up. Talking about power quality, as you know, we have a lot of power quality issues, voltage interruptions, voltage dips, over voltages, transients and so on. But we are focusing more on the harmonics for today and related to the local EV charge, and I also talk a little bit about PV systems. So we go now to the challenges in increasing PV and EV. And to show you what challenges we have in the grid operator, I will demonstrate it just in a simplified way. Maybe it's not technically perfect, but I hope at the end you understand a little bit about the challenges we have as an operator. So we have a small grid. We have here 10 kV grid on the left side. Then we have a transformer. It transforms the voltage to 400 volts. So there we have our low voltage grid, and in this grid we connect two chargers. And if they are charging, it will be a current flowing. To get this flowing, you need a voltage, of course, but to have this current, you need also a ball has to be running. It's a ball from a hill to the right. So there must be a kind of slope to have a flow, and the slope is, let's say, the voltage. So in the beginning it's 400 volts, for example, and at the end, let's say it's 360 volts. So there must be a voltage difference to have a flow. In the opposite way, if you have a source, you have also the idea. The current has to be flowing, and you have to have voltage difference. So if the 400 volt is on this side, that means on this point we need a higher voltage. If this G2 also is a source, you need a higher voltage. So for example, at your home, if you have a neighbor who has connected PV panels on the roof, maybe this is a neighbor, he don't have problems, and maybe you have problems because your voltage is too high. You need this voltage difference again. You know? So to have this complete slope, you have the current is flowing. Now we have a grid which is not only low voltage but also medium voltage. And in this grid we have sources. We have a big PV installation. On the medium voltage grid we have a transformer which transforms the mid voltage, for example 10 kV, to the low voltage side. In the low voltage side we have the panels on the roof, and we have the charger at the end. So looking to the voltage profile, it could look like this. This is the profile. So as we now learned that on the points where you have generation, the voltage must be higher. It's like the hill. And also here, the voltage on this point must be higher to have a flow. And also, if you have a load, that's the opposite way, it's going down. So there you have your voltage profile, and in this voltage profile, the operator has boundaries. It's about, well, in this case, 0 of 1.1 nominal voltage, and the top and the low side is 0.9 of the nominal voltage. So this is the 50 Hertz. Now we're going to more the higher frequencies. And we're talking about higher than 50 Hertz and lower than 2 kHz. This is our frequency range right now. Then you have the sources again, but now the charger is also a kind of source, caused by this switching of the inverters or the electronics inside this charger. So now the charger is a source too. And then the voltage profile is different, and is also much lower than the nominal voltage, but we have a kind of profile. And we talking then not about voltage, but more about harmonic voltages, and we're talking about total harmonic distortion, for example. And we as an operator has a limit, and that is 8% of the total nominal voltage. So, if you want to know what the voltages are, we can calculate it on different points. We cannot measure, we don't have measurements. So we calculate it, and let's say these balls, let's say, or bullets, is calculating the total harmonic distortion of each point. There you see it, and here it's almost at 8%, and there you see it's touching the 8%. You see here some diagrams, and that gives you the voltages of each source. So this is the diagram of the source of a PV installation, and there you have from the panels, and there is from the EV charger. So in the presentations this morning, they talked almost only on the diagrams of the component itself. But the operator has all these interactions in the grid. So this sources makes a behavior in our grid. And that is what we have to know. But not only of the component itself, but what are the interactions with the grid, and what are the interactions between these sources. That is for the operator the most important issue. So in total, grid has also this kind of profile. It's different. In this case it's the same, it's an example, but it will be different than all these separate components. It depends. It can be bigger or more than there, and these sources also less. It's depending on the interaction between them, and also the interaction with the grid. So that's what we have to observe. This phenomenon is more like, we know so many years, and one of them is a kind of flicker we know, and this is from our customer, and they have really this kind of flicker in their own restaurant. You know, it's, I think from 1 year ago, we have this movie from a customer of us. So we comply with the regulations, but the customer has some problems. So we want to detect this before they have this problem. So till now, all these what I'm talking about is in it's available in a book. All these events, all these issues. It's from Chef Coben. He's also talked this morning, and well, this is a manual in Dutch, but also I think there is a manual in English version. So Chef made a book about all these issues. Now we come to more the higher frequency range, and now we're going to more we call it the HIPRA of the supraharmonics, and that is a range between 2 kHz and 150 kHz. We have the same grid again. We see also the sources again, and also the interactions, and we have here the total harmonic distortion again. Now we get these bullets again, but now we see it's different. There it goes higher than 8%, and it's more diverse. And how is that possible? It comes that the frequency going higher, and that makes also another kind of impedance pattern, and that is what I want to show you now. So this impedance, this is the graph, and there we're starting at 50 Hertz, the impedance of the grid, and you see the impedance is really like resonances. It's going up very high. So if the frequency is going up, the impedances will be higher, but it's not linear, but there is some oscillations too. So we as an operator have to know about this impedance. Why? It's the Ohm's law. You know, if you know the source, and that is, I think, we measure that. You saw the presentation this morning. We have some knowledge how we can calculate the source. Now we have to know the grid impedance. That's the operator's responsibility to have a grid impedance. And with that, we can calculate the harmonics, the voltage harmonics. And every harmonic voltage harmonic, if you know that, we can measure that, and we have an emission limit. So we can give to the customer a limit that you say, if this is your source, the limit must be like this. If we know the limits of all these harmonics, we are in control, because there will be no disturbances at other customers. So that's about the challenges. Now we're going to more the harmonic emissions. Because why is that so important? So let's see how that works at pollution, the CO2. You know, this problem with the farmers, you know, the emissions is kind of trading, as you know. We have a limit, as the Netherlands, and it decreases every year. So in total package on pollution, there is a kind of limit, and every industry has a part of it. So you can compare with power quality. It's not pollution, but it's harmonics. And this harmonics makes this, you need some emission limits that is not too high. So, for example, we connect 130 MVA wind farm on 66 kV in Maasvlakte. And there you have the pi. We call it the pi. It's the total emission limits of what is what the regulations gives us. A part of it is TenneT's responsibility. Then a part is from Stedin, that one, and also that one. It's the color of Stedin. And a part is of the wind farm. So in all these parts, that is all, let's say, industry which makes this kind of pollution. And the wind farm gets its own limits from Stedin, so that we know we are not exceeding the total emission limits. So that is why it's so important that for every customer, a charger or whatever, we can tell this company what the limits will be. Otherwise, it takes the whole pie. So that's what we want. So to calculate this limit for each customer, we have these are the variables. The grid concept, is it like this, a string, or is it meshed? The length of cables is depending, resonances, what we saw in these impedances, the type of inverters, the switching frequency of PV and EV charger, and also the amount of it. This is free, but if it's more, also gives limits on the emission. So how we can calculate that? Then we need tools for that. We cannot measure it always, and also not in every place, so we have to calculate it. So, summarized. More EV chargers, but not only EV chargers, but also PV, leads to uncertain high frequency behavior at medium and low voltage grid. Study is needed to determine impact EV at medium and voltage grid. Injection of emission limits injection of emissions are needed, interactions, and then we can calculate the emission levels, and if needed we can also make some solutions. So we need to do study, and the study we are using PowerQuality mostly as a standard analyzing tool, and this tool, this PowerQuality from Dixieland, there you have frequency dependent models, you have harmonic low flow calculations, you can do frequency sweep calculations, and using the measurements and the knowledge we learned this morning, we can detect the possible exceeding harmonic emissions in the network, and also making the solutions. To make this study, you have two directions to model this charger. You can do it using functional markup interface, and that means that you can use, you have model, for example, a model at Simulink, and you can convert it into the Dixieland model PowerQuality. So there you have a kind of black box of a charger, for example, of a PV installation, and with that you can do your simulations. The second one is using Python as a script. In this Python you can also making algorithms or equations to calculate the harmonic currents, and if it's needed also voltage dependent. That is, I think, a requirement. So with one of these two directions you can study this. That is our goal. Now we go to the wrap-up. So to have this in control, all these kind of events, and also to comply with the regulations, you need to do monitoring, do some analysis, predicting it by studies and simulations, and at the end we can make the solutions if needed. Well, thank you for the attention and have a great day.